In today's video, we are diving into one of the wonderful physical phenomena of nature. Do you know that if you flash a light on a material surface, you can knock off some electrons from the surface and observe a small current through the circuit? Yes, this wonderful physical phenomena was first observed by Heinrich Hertz in 1887 and later experimentally confirmed by Leonard in 1902. How do you explain this phenomena scientifically? In 1905, Einstein published his paper explaining this phenomenon theoretically in his famous photoelectric theory, which won him the Nobel Prize, in which he explained the photoelectric effect in detail, proposing the dual nature of light. What is the scientific meaning of the dual nature of light? In simple words, the dual nature of light means light can behave as both a particle and a wave. How do you prove that light is a wave? What are the wave-like properties? Light behaves like a wave because it can bend around obstacles and spreads out after passing through slits, which is known as diffraction, and it is one of the properties of the waves. Light also behaves like a particle. As it travels in a straight line, it can eject electrons from a material surface when it strikes it like a particle, which is known as photoelectric effect. Then what is photoelectric effect in a nutshell? Photoelectric effect is a physical phenomenon. When light is flashed on a material, it causes the electrons to be emitted out of it. The electrons that are emitted out are called photoelectrons. What are the observations made during research on photoelectric effect? The first observation is that the velocity of the emitted electrons depend on the frequency of the incident light and not its intensity. The second observation is that the photoelectric current is proportional to the intensity of the incident light. The third observation is that there is a minimum frequency called the threshold frequency, below which no electrons are emitted. The fourth observation is that photoelectric emission is instantaneous, meaning that the emission of electrons happens only at the instant when the light is incident on the material. Based on these observations, Einstein published his photoelectric equation. He proposed that the electrons in the material don't absorb radiation continuously. Radiation energy is made up of discrete units called quanta of energy. The word quanta means in discrete quantities. He stated that the kinetic energy of the emitted photoelectron is equal to h times mu minus mu naught, where h is Planck's constant, mu is the frequency of the incident light, mu naught is the threshold frequency of the material. What is the threshold frequency? The threshold frequency is the minimum frequency of light which can eject a photoelectron from a material surface. It is the characteristics of the material. If the incident light has frequency below the threshold frequency, no electrons are emitted from the material. What is stopping potential? The stopping potential is the minimum voltage needed to stop the most energetic photoelectrons emitted from a metal surface when it is illuminated by light. Essentially, it is the potential difference required to reduce the current of photoelectrons to zero. The stopping potential is independent of light intensity. In contrast, the saturation current is proportional to the intensity of incident radiation for a given photosensitive material and the frequency of incident radiation. Effect of frequency of incident radiation on stopping potential is expressed as Kmax equal to E times V naught, where Kmax is the maximum kinetic energy and V naught is the stopping voltage. What is work function? The work function is the minimum amount of energy required to remove an electron from the surface of the material. This energy threshold is crucial because only photons with energy equal to or greater than the work function can eject electrons from the material's surface. The work function can be expressed mathematically as phi naught equal to h times mu naught. Now we shall do some exercises based on this topic. In exercise 1, is it possible to say photoelectric effect with red color incident light? The energy required to rip an electron depends on the work function of the material. the photons of red light lack this energy. The energy of the incident light depends on the frequency and not on the intensity of the incident red light. This demonstrates the particle behavior of light. In exercise 2, the work function of a material is 3.1 electron volt. A light of frequency 10 to the power 15 Hz is incident on it. Calculate the incident wavelength and find out if photoelectric emission occurs or not. Phi naught equals 3.1 electron volt, which is equal to 3.1 into 12.6 10 to the power minus 19 joules. Mu equal to 10 to the power 15 Hz. Lambda naught equal to wavelength equal to Sc by phi naught and lambda equal to c by v, where c is the velocity of light and mu is the frequency. Using the formula 1, lambda naught equals 4.01 into 10 to the power minus 7 meters. Using the formula 2, we find that the wavelength lambda equal to 10 into 10 to the power 8 divided by 10 to the power 15, which is equal to 3000 angstrom. Since lambda is smaller than the threshold frequency, photoelectric emission will occur. So, the incident wavelength is 3000 angstrom and the photoelectric emission will occur. In exercise 3, when a light of wavelength 4000 angstrom is incident on a photoelectric material, photoelectrons are emitted. For another emitter, a light of wavelength 6000 angstrom is sufficient for photoemission. What is the ratio of work function of these two materials? We have phi equal to Sc upon lambda naught. And using the case 1, where lambda 1 equal to Hc upon phi 1, and in the case of case 2, lambda 2 equal to Sc upon phi 2, divide equation 1 by 2. Lambda 1 by lambda 2 equals phi 2 divided by phi 1, that is equal to 6000 angstrom divided by 4000 angstrom equal to 3 by 2, which is equal to 1.5. The ratio of wavelengths equal to 1.5. In exercise 4, the threshold frequency for a material is 10 to the power 15 Hz. Light of lambda equal to 4000 angstrom falls on it. Which of the following statements is correct? Photoemission will not take place. Photoelectrons come out with zero speed. Photoelectrons will come out with 10 to the power 3 meter per second speed. Photoelectrons will come out with 10 to the power 5 meter per second speed. Frequency of incident light equal to mu equal to c by lambda, where c is the velocity of light and lambda is the wavelength. This frequency is lesser than the threshold frequency of the metal, hence photoelectric emission will not take place. In exercise 5, the frequency for a certain photoelectric material is mu naught. When it is illuminated by a light of frequency mu equal to twice mu naught, the maximum frequency of the photoelectrons is V naught. What will be the maximum velocity of the photoelectrons when the same metal is illuminated by light of frequency mu equal to 5 times V naught? Here we have to use the equation for the kinetic energy, half m V max square equal to h times mu minus mu naught. For a light of frequency mu equal to 2 times V mu naught, we have half m V naught square equal to h times 2 mu naught minus mu naught equal to h times mu naught, which is equation 1. For a light of frequency mu equal to 5 times mu naught, we have half m V square equal to h times 5 times mu naught minus mu naught equal to 4 times h mu naught, which is the equation 2. Dividing 1 by 2, V square equal to 4 times V naught square. Therefore, V equal to 2 times V naught. In exercise 6, when a certain metal surface is illuminated with a light of wavelength A, the stopping potential is V. When the same surface is lit by a light of wavelength 2 lambda, the stopping potential is V by 3. What is the threshold wavelength for the surface? For the given material, wavelength of light used equals lambda. The stopping potential equals V. That is, lambda naught be the threshold wavelength. The maximum kinetic energy of the emitted electron K max equals hc into 1 by lambda minus 1 by lambda naught, which is the equation 1. Again, wavelength of used light equal to lambda dash equal to 2 lambda and the stopping potential V dash equal to V by 3. That means that K max equal E times V dash equal to Sc into 1 by lambda 1 minus 1 by lambda naught equal to 1 by 2 lambda minus 1 by lambda naught. It also means that EV by 3 equal to Sc times 1 by 2 lambda minus 1 by lambda naught, which is equation 2. Divide equation 1 by equation 2. We will find that 3 times 1 by 2 lambda minus 1 by lambda naught equals 1 by lambda minus 1 by lambda naught, which means to say that lambda naught equal to 4 times lambda. Therefore, the wavelength is 4 times the wavelength of light. In exercise 7, the work function of a photosensitive material is 4 electron volt. Calculate the longest wavelength of light that can cause photo emission from the surface. The work function phi equal to Sc by lambda naught. Therefore, lambda naught equal to Sc by phi and Sc equal to 1240 into 10 to the power minus 9 by 4. Therefore, lambda naught equals 3.1 10 to the power minus 7 meter, which is equal to 310 nanometer. In exercise 8, the radiations of energies 1 electron volt and 2.5 electron volt are incident on a metal surface having work function of 0.5 electron volt. What is the ratio of maximum velocities of the emitted photoelectrons? To find the solution for this exercise, we can express E1 equal to 1.0 electron volt minus 0.5 electron volt, which is equal to 0.5 electron volt. And E2 equal to 2.5 electron volt minus 0.5 electron volt equal to 2.0 electron volt. Therefore, E1 by E2 equal to 1 by 4. Therefore, the ratio of the kinetic energy of the first to the second equal to half m1 v1 square divided by half m2 v2 square equal to 1 by 4, and the ratio of velocities v1 by v2 equal to 1 by 2. In exercise 9, if a light of wavelength 350 nanometer is incident on a cesium surface, calculate kinetic energy of the photoelectrons ejected. The work function of cesium is 1.9 electron volt. Given phi equal to 1.9 electron volt, lambda equal to 350 nanometer. Therefore, HV equal to 1242 nanometer electron volt divided by 350 nanometer, which equals to 3.5 electron volt. Therefore, kinetic energy, which is maximum, equal to H mu minus phi equal to 3.5 electron volt minus 1.9 electron volt. Exercise 10. The threshold frequency for a certain metal for a photoelectric effect is 1.7 10 to the power 15 Hz. When a light of frequency 2.2 10 to the power 15 Hz is incident on the metal surface, the kinetic energy of the emitted photoelectrons is 3.3 10 to the power minus 19 joules. Calculate Planck's constant. Given mu naught equals 1.7 10 to the power 15 Hz, mu equal to 2.2 times 10 to the power 15 Hz. Kinetic energy is given, which is equal to 3.3 10 to the power minus 19 joules. we have to substitute in the equation wherein half mv max square equal to h times mu minus mu naught. Therefore, h equal to kinetic energy divided by mu minus mu naught, which is equal to 3.3 10 to the power minus 19 divided by 2.2 10 to the power of 15 minus 1.7 10 to the power 15. Therefore, Planck's constant h equals 6.6 10 to the power minus 34 joules second. We have reached the end of the video. Thank you for watching.